The following scenario is hypothetical and presented for educational and entertainment purposes. Imagine you are standing on the deck of a research vessel at night, staring into black ocean water that looks calm enough to nap on. The surface barely moves. Nothing dramatic. No sharks leaping, no glowing monsters, no cinematic music. Just the quiet, patient sea. And somewhere down there, sliding along the mud like a sleepy piece of spaghetti with opinions, lives one of the strangest engineers in the animal kingdom. At first glance, the creature in question seems almost disappointingly plain. Long, pinkish, a face that looks like it forgot to finish evolving. No jaws, no impressive teeth, no armor. If you were designing a survival machine from scratch, this animal would probably fail the first brainstorming session. And yet, this humble organism has perfected one of the most outrageous defensive systems in the natural world. The hagfish. Now, before the word slime makes you wrinkle your nose, let us slow down and look carefully. Because this is not just any slime. This is a biochemical ambush system, a microscopic trap, a weaponized cloud that turns the simple act of biting into a catastrophic mistake. Picture the moment from a predator's point of view. Perhaps a hungry fish notices the soft, worm-like shape crawling along the seafloor. Easy meal, no armor, no speed, no teeth worth worrying about. The predator lunges, mouth opening wide, water rushing across delicate gill structures that must stay clear if breathing is to continue. Everything about the attack seems routine. Then the hagfish does something that looks almost unimpressive. It releases slime, but the word release does not do justice to what actually happens. Inside the hagfish's skin are rows of specialized glands, each packed with tiny packets of tightly coiled protein threads and mucus droplets. When disturbed, these glands fire their contents into the surrounding water, like microscopic confetti cannons. The moment seawater mixes with the material, physics and chemistry begin an explosive collaboration. The threads unravel, the mucus expands, and in less than a second, a few milliliters of glandular material transform into litters of gelatinous mesh. To the predator, it is as if the water itself has suddenly thickened into living fog. Slippery strands tangle around the mouth. The gel rushes into the gills. Water can no longer move cleanly across respiratory surfaces. Breathing becomes difficult. Panic replaces hunger. The attacker must immediately retreat, shaking its head violently to clear the clogging slime before suffocation becomes a real possibility. The hagfish, meanwhile, simply slides away. What looks like passive goo is actually a defensive system designed with shocking precision. The slime is not meant to trap enemies permanently. It does something much smarter. It weaponizes the predator's own breathing system. Every gulp of water pulls more slime into the gills, amplifying the problem. And here is the unsettling part. This entire mechanism comes from an animal that on paper appears almost absurdly primitive. No jaws, no vertebrae in the traditional sense. A body plan that biologists politely describe as ancient. Yet this ancient body carries a defense so effective that many predators have learned a simple rule of ocean etiquette. If it looks like a hagfish, do not bite it. But the slime itself is only half the mystery. Because if you were suddenly surrounded by your own defensive fog, thick, sticky, potentially suffocating, there would be a new and very awkward problem. How exactly do you avoid choking on your own weapon? And the hagfish has an answer for that too. One that involves tying its own body into a knot. Somewhere along the seafloor, in darkness so complete that sunlight has never visited, the hagfish performs a maneuver that would make a yoga instructor nervous. Imagine a creature shaped like a flexible tube suddenly looping its own body into a knot. Not metaphorically, but literally tying itself into one. At first glance, this seems like the kind of behavior that should end badly. Knots, after all, are what happen when things go wrong. Headphone cables, fishing lines, holiday lights. Yet for the hagfish, the knot is not a mistake. It is a carefully evolved piece of biological engineering. Because the moment the slime weapon deploys, the hagfish faces the same problem as its attacker. The water around it becomes thick with mucus and protein threads. Visibility drops, movement becomes sticky. Most importantly, the slime coats the hagfish's own skin. If left unchecked, it could clog the animal's nostrils or interfere with its ability to move through the water. In other words, deploying the weapon risks trapping the user in its own defense cloud. So the hagfish does something that almost looks like slapstick physics. It ties a knot in its own body and slides that knot from head to tail. Picture the motion slowly. The animal bends itself into a loop, pushes part of its body through that loop, and tightens the knot like someone pulling a drawstring. Then, using muscular contractions, it drags the knot down its length like a living squeegee. As the knot travels, it scrapes slime off the skin, wiping the body clean in seconds. It is efficient, mechanical, and strangely elegant. But the knot serves another purpose as well. Remember that hagfish do not possess jaws like most fish. They cannot simply bite and tear chunks of food with crushing force. Instead, they feed in a way that is both ingenious and slightly horrifying. When a hagfish finds a carcass on the ocean floor, perhaps a dead whale, perhaps a fallen fish, it burrows into the body like a living rope. Inside the carcass, space becomes tight. The hagfish grips tissue with tooth-like structures on a rasping plate, then forms a knot in its own body. By anchoring the knot against the flesh and pulling backward, it creates leverage, allowing it to tear off pieces of meat. The knot becomes a biological pulley system. Imagine trying to eat dinner using nothing but your tongue and a carefully tied rope around your torso. Ridiculous for humans. Perfectly reasonable for a hagfish. Which brings us back to the slime. Scientists studying this material in laboratories quickly realized something astonishing. The threads inside hagfish slime are not ordinary fibers. Each thread begins tightly coiled inside a microscopic capsule called a skein. When released into seawater, the skein unspools into a filament that can be several centimeters long, an enormous length compared to its original size. Thousands of these threads expand simultaneously. They intertwine with mucus to create a three-dimensional network that traps water like a sponge. The resulting slime is more than 99.9% water, yet behaves like a dense, choking gel. In other words, the hagfish carries hundreds of tiny compressed fiber coils under its skin, ready to inflate into a suffocating cloud the instant danger appears. It is less like a slime spray and more like a microscopic parachute factory detonating underwater. And here the story begins to take an unexpected scientific turn. Because when engineers looked closely at these protein threads, they noticed something that made them pause. The fibers were incredibly strong, flexible, lightweight, potentially useful. In fact, some researchers started whispering a provocative idea. The hagfish might be quietly producing a material that could rival spider silk. And if that were true, the ocean floor might be hiding not just a strange defense mechanism, but the blueprint for an entirely new class of bioengineered fibers. Far away from the murky seafloor where hagfish quietly roam, scientists in bright laboratories began to stare at the slime with a mixture of fascination and mild disbelief. Because once the gooey drama of the defense cloud settles, something remarkable remains hidden inside that watery mess. A network of protein fibers that behaves less like mucus and more like advanced engineering. The key lies in those microscopic coils, the skeins. Inside each slime gland are thousands of these tiny capsules, each containing a single thread packed so tightly that it resembles a miniature ball of yarn compressed by invisible hands. When released into seawater, the capsule opens and the thread unspools with astonishing speed. No motor, no chemical explosion, just clever geometry and a little help from fluid dynamics. Within fractions of a second, one thread that once fit inside a microscopic capsule stretches out to lengths thousands of times greater. Multiply that by tens of thousands of threads, mix them with expanding mucus, and the result is a tangled mesh that traps water so efficiently it becomes a breathing hazard for predators. But here is where scientists leaned closer to their microscopes. When researchers isolated the threads themselves, carefully separating them from the mucus, they found fibers that were surprisingly strong and flexible. Not metal strong, of course, but impressive for a protein structure produced by an animal that looks like it misplaced its skeleton several 100 million years ago. Under magnification, the fibers reveal a layered architecture. Long protein chains align in repeating patterns, forming structures similar to those seen in silk proteins. This arrangement allows the fibers to stretch slightly without snapping, distributing stress along the length of the thread. In simple terms, they are tough, lightweight biological cables. And that discovery triggered the first real scientific climax of the hagfish story. Material scientists began asking a bold question. Could humans replicate this fiber? Imagine a fabric stronger than many synthetic materials, produced not in petroleum-based factories, but through biological processes. Something lightweight, flexible, and biodegradable. Protective textiles, medical sutures, high-performance composites, all inspired by an animal that looks like it belongs in a forgotten corner of evolutionary history. There was just one small complication. Hagfish slime fibers are incredibly difficult to harvest. A single hagfish can produce impressive slime clouds, but collecting large quantities of intact threads without destroying their structure is messy work. Even worse, the fibers only fully form when they contact seawater and unspool properly. Trying to reproduce that delicate unfolding process in industrial conditions turns out to be tricky. Nature, as usual, makes it look effortless. So researchers shifted strategy. Instead of collecting fibers from hagfish directly, they began studying the genes responsible for producing the slime proteins. If those genetic instructions could be inserted into bacteria, yeast, or other biological systems, perhaps those organisms could manufacture the proteins in bulk. Then the fibers could be spun artificially, in theory at least. And while this line of research continues today, it reveals something quietly profound about the hagfish. What began as a strange defensive trick might also be a blueprint for future materials science. But if you return your attention from the laboratory microscope back to the ocean floor, the hagfish itself remains delightfully unconcerned with human curiosity. It continues its slow, secretive life in the deep, slipping through sediments and carcasses with ancient patience. Predators still occasionally attempt a bite. The result is almost always the same. A sudden underwater blizzard of slime, a panicked fish coughing out gelatinous threads, and a pink ribbon of hagfish quietly tying a knot in its own body before disappearing into darkness. Which leads to the second and perhaps deeper climax of this strange story. Because the more scientists study hagfish, the more uncomfortable a realization begins to form. This animal's body plan, jawless, boneless, slime-filled, looks primitive only from a human perspective. From an evolutionary standpoint, it may be something far more unsettling. Not a failed design, but a survival strategy so effective that it has barely needed to change for hundreds of millions of years. If you could travel backward through geological time, past the rise of dinosaurs, past the first forests, past the moment when animals first crawled onto land, you would eventually reach ancient oceans filled with creatures that look almost alien to modern eyes. Armored fish drift through murky water. Early vertebrates experiment with spines, fins, and jaws that have not yet perfected their grip on the world. And somewhere among them, sliding quietly through the mud, you would recognize something strangely familiar. A hagfish. Not exactly the same species, of course, but unmistakably similar. Long body, jawless mouth, rows of slime glands waiting beneath the skin like microscopic emergency devices, which leads to the slightly mind-bending second climax of this whole investigation. The hagfish body plan has survived for hundreds of millions of years with only modest changes, while other lineages exploded into sharks, reptiles, birds, mammals, and eventually humans arguing on the internet. The hagfish simply continued being a hagfish. Evolution did not forget it. Evolution tested it repeatedly and apparently shrugged. From a scientific perspective, that endurance tells us something important. When we imagine evolution, we often picture constant improvement, like software updates marching toward perfection. But evolution does not aim for elegance or complexity. It aims for survival that works well enough to continue. The hagfish's strategy happens to be brutally effective. Consider the whole system together. The animal has a flexible, eel-like body that can slip into narrow spaces where predators cannot easily reach. It feeds on carcasses that sink to the seafloor, food sources many animals ignore or cannot access. Its knot-tying trick provides mechanical leverage in the absence of jaws. And hovering above all of this is the slime weapon, a defensive system that weaponizes the breathing mechanism of any attacker reckless enough to bite. The brilliance of the slime is not in brute force, it is in timing and physics. Predators must move water through their gills constantly. The hagfish slime interrupts that flow instantly. It transforms the predator's own respiratory system into a vulnerability. The attacker is forced to retreat, not because it is injured, but because continuing the attack risks suffocation. Few defenses in nature are so elegantly unfair. Even sharks, which possess powerful jaws and formidable hunting instincts, have been observed abandoning hagfish after encountering the slime. The cost of continuing simply becomes too high. Meanwhile, the hagfish calmly wipes itself clean with its traveling knot and glides away as if nothing particularly dramatic just happened. And perhaps that is the most delightful twist in this strange scientific story. When humans first encounter hagfish, our reaction tends to be immediate disgust. Slime is messy. Knots in one's own body look unsettling. The feeding habits, burrowing into carcasses, sound like something designed to ruin dinner conversations. But if we step back and examine the system scientifically, the creature begins to look less like a biological oddity and more like a masterclass in minimalist engineering. No armor plates, no speed records, no spectacular teeth, just a soft body, a knot trick, and a slime defense so effective that predators learn quickly. This meal is not worth the trouble. In a way, the hagfish exposes a quiet bias in how humans imagine life should work. We tend to admire sharp claws, powerful muscles, dazzling colors, the dramatic tools of survival. The hagfish chose a different path. It turned mucus into a weapon. And in doing so, it solved the ancient problem of survival with a strategy so strange that if humans had invented it, we would probably assume it was science fiction.